Okay, so chapter 3, section 2 gets a little bit more complicated in things they talk about. The first thing they talk about in chapter 3, section 2, part A is radioactivity. Now, this is not a huge topic we are really going to get into. That comes later in chapter 13, which I don't even think we touch in this class. But just know that there are three major types of radioactivity. So when something is radioactive, an atom is radioactive and it decays, it can give off either an alpha particle, a beta particle, or a gamma ray. An alpha particle is basically the nucleus of a helium atom, helium nucleus. It has a +2 charge because of the 2 protons, and it has a mass number of 4, which is the 2 protons plus the 2 neutrons. A beta particle is basically an electron. It has a -1 charge, and because electrons have such tiny mass, we say the mass number is 0. Electrons do have a mass, but they're just so tiny compared to a proton. Gamma ray is just pure energy. Okay, it has no charge, it has no mass, it is pure energy. And it acts like a wave. So that's all they really talk about radioactivity. But this radioactivity helped us discover the different structures of an atom. In fact, for the electron, this was not in the reading, but I'll talk about it anyways. In 1897, after Dalton did all his stuff, J.J. Thomson proposed the idea of electrons, which he discovered through the use of a cathode ray tube. Basically, this cathode ray gave off this green beam, which essentially is the beta particle. And this green beam he discovered was attracted to a positive metal plate. And since it was attracted to the positive plate, he figured this green beam had to be composed of negatively charged particles. Then after a lot of calculations, he discovered that this green beam, these particles, actually weighed less than hydrogen. Well, hydrogen's the smallest atom, the smallest element. So if these green beams weigh less than hydrogen, that means these particles are smaller than an atom, which at first was thought to be the smallest thing ever. So he discovered that these electrons are actually smaller than an atom, which means atoms have smaller pieces. An atom is divisible. It's not indivisible, it is divisible now. It can be divided. And he came up with what's called the plum pudding theory, which basically an atom is this huge positive sphere. Okay, it's just a uniform positive sphere with different pieces, or not different, but electrons spread throughout. A lot like plum pudding, which I show you here. So the entire bread is the actual positive sphere, and in each piece of raisin, which is what these are plums actually, plums and raisins, but these are plums, are the electrons. So this is what an atom looks like according to Thomson. Then one of his students, Ernest Rutherford, did the gold foil experiment. Now Rutherford totally hypothesized and totally predicted that if atoms kind of look like plum pudding, then all the alpha particles he shoots that piece of gold foil will go straight through. Now before I get any further, please understand that a scientific model is not exactly what something looks like. Models are used to help us visualize observations that we make. This is not what an atom looks like. And when we get to Rutherford's model, that is not exactly what an atom looks like. No one knows exactly what an atom looks like. We just create models that help us visualize the observations that we make in the laboratory. So again, Ernest Rutherford's gold foil experiment. So Rutherford shot these alpha particles, which we talked about earlier, through a very thin piece of gold foil. And he totally predicted that all the particles would go straight through. But we'll discover that didn't happen. In fact, his observations were the following. A vast majority of the alpha particles did go straight through the gold foil, which he predicted. Almost all of them went straight through the gold foil. Some of them veered off at slight, very slight angles, which he kind of predicted because of the positive and negative charges. If alpha particles were positive, they would be attracted to the negative electrons and they would repel from the positive sphere that he believed existed. But something incredible happened. Extremely few, about 1 out of 10,000, I've seen it say 1 out of 8,000, but 1 out of 10,000 particles deflected at very large angles. Some of them even deflected straight back. Okay, this could not believe happened at all. This was completely crazy. So what explained this? Why did most of the particles go straight through? Why did some of them veer off at slight angles? And why did extremely few of them deflect at large angles or even bounce straight back? Well, he came up with this conclusion. The reason why most of the alpha particles went straight through the piece of gold foil was because atoms are mostly empty space. Atoms are like 99.95% empty space. There's just nothing there. Some of the particles, veered slightly because of the positive and negative charges. Again, you have this alpha particle here, it gets close to a positive charge and it's going to repel, and so it's going to veer off at a slight angle. Or it gets attracted to the electrons and again, veers off at a slight angle. But what set Rutherford apart from everyone else, what explained the reason why some of these alpha particles bounced straight off the gold foil, was because atoms have an extremely small, yet very, very dense center called the nucleus. These are where all the protons are located. So all the protons are located in the nucleus. Note that they have not discovered neutrons yet. That would not be discovered for another about 20 years from now. This would happen, the gold foil experiment happened about 1911. So roughly about 1932 is when they discovered the neutrons. But all the positive charge is located right here in the nucleus, and it's extremely dense, very, 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 very dense. So these alpha particles would go towards the gold foil, hit the nucleus, and bounce straight back. Or it can hit the side and go off at a very large angle. So again, Ernest Rutherford was able to create this model to help explain his three observations. Again, his observation was most of the particles went straight through, which he explained was because atoms are mostly empty space. Some of the particles veered at very, very tiny angles. Well, that was because of the positive and negative charges. And again, very, very, very few had very large angles or bounced back, and that was due because of the very, very, very tiny nucleus. Now, later on, we'll discover that this model, which does explain those observations, is not the best one, because it doesn't explain other things, so other people make other models. And that's it for Chapter 3, Section 2.